Welcome everyone. This is our 6th Cyberseminar in the 2020 Cyberseminar series. I'm Christina Bandaragoda and I'm joined by our Waterhackweek student director this year, Stephen Pastrana. Do you want to introduce yourself, Stephen?
Hi, yeah, I'm Stephen Pastrana, PhD student at the University of Washington.
So I just want to remind everyone that you can chat with us after or during the Cyberseminars on the Slack channel. We have a forum here, and if you are already on the Waterhackweek Slack, the Cyberseminar channel is the best one to go to. So our panelists we have today are going to talk with us about scaling climate data and hydrologic processes. Now, Bart Neeson is the leader of our computational hydrology group at the University of Washington, and Yinfan Zhang is in charge of the Zhang Stream Lab at the University of Hawaii at Manoa. And both Bart and Yinfan are faculty alumni of Waterhackweek 2019. And what we're going to talk to them about, or hear from them about, and then discuss, is how do we, in their career-long experience, think about all of the uncertainty that they've been working on regarding climate data and how these climate inputs that go into our hydrologic models, how does it affect our ability to understand the hydrologic processes we're trying to simulate? And on top of that, explaining all of the uncertainties and sensitivities that we study in our research, how do we communicate all of that to the public? Because when you're scaling from a global climate change data set to inform decisions at local scales, it sounds great conceptually, but as most of us on the call know, it's very complicated research, in fact. So part of that research is so much has been accomplished in the past few years that Yinfan and Bart are going to talk to us about, and hopefully get us to where is the frontier of what we know and don't know about scaling methods and using climate data to understand climate change and how humans adapt. So Bart, do you want to take the intro from here?
Yep, no problem. All right, so thanks, Christina. My name is Bart Neeson. As Christina said, I'm here in civil engineering, and for much of my career, I've looked at modeling of very large systems, like entire continents. Way back, I did some global simulations and so on. And as part of that, I've also looked quite a bit at climate change impacts on hydrological processes at kind of large basin scales. So, I mean, Christina obviously posed a lot of questions, and I was given about 7 to 10 minutes to talk. So rather than trying to cover all that, I think we can come back to some of that in the discussion at the end of the seminar. And I actually wanted to talk more in my own presentation here about the different sources of meteorological data that we actually have and kind of the requirements of a lot of the models that we use these days. I mean, there's nothing surprising in this particular slide. It's a slide from the USGS, which basically shows the water cycle, right? And the reality is that the atmospheric conditions, or the forcings, or the time varying boundary conditions, very much constrain kind of the hydrological processes at the landscape. And if you would have to kind of take the single most important input that for a lot of systems governs much of the variability at the surface, it would be precipitation, right? And where we're going in a lot of the hydrological models, next slide. Christina, thank you. So where we're actually going with a lot of hydrological models is more and more spatially distributed models at higher and higher resolution. This picture actually shows a simulation with PARFlow, which is a hydrologic model that actually looks mostly at the subsurface. And Reed Maxwell at the Colorado School of Mines is a big partner in that type of projects. And the map that you showed shown here actually shows the depth of the water table over the entire or a large part of the United States at a very high spatial resolution. And clearly, if you actually want to run models at this type of spatial resolution, you also need to have inputs that kind of exist everywhere for the duration of your simulation, and that provide a reasonable approximation of the weather conditions at the surface. Next slide. This is another example. This is actually from the Climate Toolbox, and this is a project with which my group is involved as well. And it's actually run by John Abatsoglu and Catherine Hegewisch at the University of Idaho. And it basically provides kind of near real-time conditions of what is happening at the land surface. And on the meteorological data that they display, they provide a lot of different kind of way to interpret meteorological data. And so, for example, this is the precipitation anomaly, so the difference from the long-term mean since January 1st of this year, right? I downloaded this particular picture yesterday. The data here is basically at 4 kilometers over the entire continental United States. And what you can see is that California has been dry, the Southeast has been pretty wet since the start of this year, and the West Coast here in the Pacific Northwest has been very wet, which I personally can attest to as well. Although the last 2 weeks have actually been very nice. All right, so next slide. Okay, so this is me.
That's your, now we're into the rest of your slides and.
Perfect. All right, so this is me, next slide. Okay, thank you. So as I said, right, like if you run hydrological modeling, and that can be all different types of models. These can be more conceptual models, or maybe more physically based models, or these days, maybe even more machine learning type based models. You basically need atmospheric inputs, which provide your time varying boundary conditions. And if you look at hydrological models, at the very least, they typically require precipitation and temperature, right? And the time step at which they require these variables or these quantities depends on kind of the model time step that you're using and so on, but you often need them at a daily or even a sub-daily time scale. Now, depending on the type of model that you're running, you may actually require more inputs than just precipitation and temperature. So you may also need short and long wave radiation, some measure of atmospheric humidity. So that could be, relative humidity, vapor pressure deficit, vapor pressure, specific humidity. There are many different measures, but you can kind of calculate one from the other with the, sometimes you need temperature for that as well. And then wind speed. And it's actually kind of hard sometimes to figure out, okay, where do you get started? Where do you get this data from? The figure here on the right is actually total precipitation over the last 5 days from another data set that's available, which is from the PRISM project at Oregon State University. All right, next slide. So, okay, so what are actually the sources that we can use for all this, creating these data sets that are useful for input to models, right? So in many ways, the gold standard still are station observations, right? So these are observations made at a single location of things like precipitation, temperature, sometimes radiation, wind speed, and humidity. On the right-hand side here is actually an experimental site at the Dutch Meteorological Institute. And you can see they actually have lots of different sensors and some duplication of sensors as well, partly because they're just testing and evaluating sensors. But station observations often are challenging to put into models directly, right? You have mission data. I mean, no matter how good your measurement program is, things break. And so, not all observations are always available. You often have missing variables in the sense that a lot of stations don't measure everything. For example, while there's a lot of stations that measure precipitation and temperature, radiation is actually measured at only a few sites. You have to do data quality control, which can be challenging. There's often a limited length of record, although like this station on the right-hand side is operated for a very long time. The period of record, the station may no longer be available. So it may have a really long record, but that record may still not be overlapping with the period for which you're trying to run your model. And then the question really is whether how representative your station is of the area that you're trying to model in your hydrological model. So while station observations are really useful and actually are the basis of a lot of the products I will describe next, they do still come with their own challenges. Okay, next slide. So for a lot of modeling efforts these days, we're basically relying on gridded products. And so gridded products, I basically mean that there's some regular spacing in space, right? So maybe you have it every 4 kilometers or every so many arc seconds. And the data is kind of regularized. There's no missing data or no missing values, I should say. And there's many different sources of that. Some of them are purely station-based. So people take station data, quality control that, fill for missing data, and then basically use some interpolation algorithm. Now that interpolation algorithm can be fairly sophisticated. It can, for example, take into account elevation and so on, but it's still basically just an interpolation. Nowadays, you actually also have data sets that are purely satellite-based. So, you know, you can, for example, measure cloud top temperatures and passive microwave emissions from the atmosphere and use that to infer precipitation. They're model-based estimates for example, all the ones that we use for climate change applications basically come from global climate model simulations. And these global climate simulations for the future don't really incorporate any observations, right? Because we don't have them yet. They may have used observations to develop some of the algorithms and so on in these models and some of the parameterizations, but there are no actual observations involved with making these future estimates. And then a lot of these gridded products are actually combinations. For example, people use satellite-based products and then correct that based on observations. For example, you can make satellite-based precipitation estimates and then correct that over land based on station observations. And then there's also model-based products that use data assimilation, and these include reanalysis products, and I will really briefly mention those. All right, next slide. So station-based products, there's a whole bunch of these. Prism I already mentioned, is probably one of the better known and one of the older ones. It exists over the entire United States and for some other areas as well. It's updated in near real time. DayMat is kind of similar. It's a gridded station-based data set. GMAT is also a gridded-based station data set. It's a little bit different than the other two. It's actually a coarser resolution, but they actually create 100 ensembles of the that basically try to account for station error and error in the interpolation method itself. So instead of getting a single precipitation value or a single temperature value for a given day, you actually get an ensemble of 100 values. And then there are blended products like GridMat, which is put out by the University of Idaho. And I just put the links here. I don't have time right now to go into all of these, but feel free to ask questions about them. On the right-hand side here is an example of that GMAT data set. It basically in the top row, in the left column, shows June precipitation from 2 different ensemble members. So these are 2 different precipitation values for June of 1993, both of which are equally consistent with the underlying station data, right? That's the important part here. The top right is the ensemble mean over all 100, and the bottom right is the standard deviation. June 1993 was picked in this case because there was big flooding in the upper Midwest. All right, next slide.
Oh, Bart, I had a quick question on the grid cell size of the map we're looking at.
So this one is 1/8 of a degree, so about 10 kilometers, 6 miles.
Okay.
So gridded products, this is actually an iMerge product. So that's actually a satellite product. And it basically is available for the entire globe at fairly high resolution. And they make real-time or near real-time products available at kind of a 3-hour lead time interval. As you can see, it actually covers the entire globe, not just the land surface, but also the ocean. And it basically is constructed from a series or a whole constellation of different satellites. So they actually, to produce this map, they take data from a whole series of satellites and merge that into one single product. As part of this satellite product, and this one was actually from yesterday afternoon, as part of this satellite product, they also have data products that actually overland inject station-based observations to constrain and optimize the satellite-based product. Next one. The challenge, of course, with a product like this is that it only exists for the time that satellite observations are available, right? Then there are gridded products that are entirely model-based, as I already said. For example, the ones in CMIP6, which is the modeling project that basically provides the data for the IPCC reports, right? We basically have kind of all the forcings that we need, but climate model output comes with its own challenges. It's often very coarse, although we're going to higher and higher resolutions. As you see on the right-hand side here, this is a visualization from the E3SM. It's the Department of Energy climate model here in the US. And you can see all these ocean eddies and so on. But really, like, you know, it looks beautiful and very high detail, but it's still, this is the entire Atlantic Ocean, right? And the spatial resolution of these simulations is still pretty coarse. Although some of these models, like for example, E3SM, can actually use variable resolution. So it doesn't have to be the same everywhere on the planet. And they can, for example, put higher resolutions over mountains than over, you know, big plains and so on. The challenge with climate data, data from climate models, is still that it's often biased, meaning it has systematic errors in it that don't make it necessarily suitable for immediate insertion into hydrologic models. And the spatial resolution is still rather coarse in many cases. So you often have to post-process this data through a process called bias correction and downscaling. And that's kind of a whole science in its own right these days. All right, next slide.
I can't move past this slide. It's so pretty. Okay.
My time is running out. Okay, so the other one I mentioned is reanalysis. So reanalysis is kind of an interesting product. So it's a model-based product, but actually in surface observations, and actually I should say surface observations, atmospheric observations are ingested into this modeling simulation to kind of keep the model running, to keep the model deviating too far from actually what was observed. They actually typically do not, that process is called data assimilation. And so in data assimilation for these reanalysis products, they typically do not assimilate surface stations. They actually do upper atmosphere, radio SON data, and so on. But the idea basically is that you run a model, for example, the same type of models that we use to do weather forecasting. So they tend to be high resolution or relatively high resolution. And then you fix the model version and you run the model for long periods of time. And that's important because when you take the output from regular forecasting models, so numerical weather prediction models, these models get improved all the time. And so if you take a time series that comes out of these models over a 30-year period, you actually have a product that changes because the underlying model has changed. So what they do is they go back to, like, you know, 1900, and they take all the observations that they can find to ingest, and they run the model forward on a daily basis, and every day they inject these observations. And these products have actually become quite good, and in many cases perform as well or better than the station-based data. So there's a new one coming out right now, ERA 5. ERA 5 is produced by the European Center for Medium Range Weather Forecasting in Europe. And they actually have a land reanalysis that has a spatial resolution of 10 kilometers. That product is currently being released. There's other reanalysis as well. MERA is a product from NASA, and there's an NCEP reanalysis. All of these reanalysis products are actually updated in near real time. So you can typically get it up to like yesterday. All right, so last slide, next one. So of course, like, you know, there's lots of different of these gridded products available, but fortunately the community has kind of standardized on the formats that they're using to disseminate these data sets. One of those formats is called GRIB, which is actually hard to use, and it's used a lot in the atmospheric sciences community, or the real-time, I would say, weather forecasting community. The other one is actually NetCDF, and that's the one that my group typically uses to interact with data products like this. And in Waterhackweek, we'll actually talk a little bit more about this data format. There's also conventions, metadata conventions that most groups start to kind of standardize on, and that also help to kind of really interpret this data. And there's some really good tools available to interact with these very large data sets. One is NCView, which is just kind of a quick viewer of NetCDF data sets, and you can kind of browse the data sets and make little plots for yourself. And then Xarray is actually a Python package for manipulating n-dimensional array. Basically, think of it like data cubes. But they can be, high dimensional cubes. Like you can have like lat long elevation from the surface and time, right? You can have many more dimensions than that. And we'll also actually go into Xarray during the Waterhackweek. And with that, I'll pass it off to the next speaker.
Thanks, Bart. I appreciate that you ended on a hopeful piece of code that at Waterhackweek, we'll, on Tuesday, we'll be able to work with some of these data sets and make amazing visualizations and build the skills to work with some of these data sets.
Yep.
Next we have Yinfan Tseng.
Hi, can everybody hear me okay?
Perfect. Yes, thank you for joining us.
Yeah, of course. So hi everybody, my name is Yinfan Tseng. I'm an assistant professor in the Department of Natural Resource and Environmental Management at the University of Hawaii at Manoa. Thank you, Christina and Tony, invite me to join this webinar. And specifically, I want to provide my perspective of my experience and my research that how Waterhackweek have been helped me and help my group. So specifically, my research coming from a more management and apply perspective. So most of my research looking at the surface hydrology and their application to stream ecosystem, as well as on other natural resource management perspective. And I appreciate Bart that is providing all the bigger, large scale perspective on all the hydrological model, as well as the meteorological forcing. That's so important. And in the following, gonna drill down to provide some perspective from a more local and regional scale management application. So next slide. So specifically, I want to orientate you about Hawaii. So that give you some perspective, that type of the regional and local system, hydrological system that me and my group are dealing with. Specifically, so Hawaii in the center of Pacific, we have 376 perennial stream, mostly orientated on the windward side, which is the northeast side of the islands. So we have 5 major islands from west to east, and from older and to very new volcanic islands. And we have this really large distribution that have different kind of seasonal pattern, as well as they have different spatial patterns that's showing. So on the northeast side, we have this perennial stream, while on the leeward side that we have those intermittent streams. Next slide. And just to give you some perspective on that, some of the management application on the hydrology in Hawaii. So we have those very unique endemic aquatic species that in Hawaii that is only exist in Hawaii. And what even unique about them that is they are a physiognomous species. What that means is that they born in the headwater stream, they floated down drift to the ocean, stay there from 3 to 18 months. And when there is a flash flood like coming out that sensing as the signal for them, they migrated back to the headwater stream. And specifically, you can see that on the bottom right corner that is showing the river mouth that is sending the freshwater signal for our freshwater species to come back to their natal stream. And it has been observed for all our amphibious species. So next slide. So that tied it into why this hydrological modeling or this understanding of how the hydrological response to our watershed is so important. So first you see those big different patterns in the spatial orientation of those streams and the watersheds. And then you know that we have this unique environmental system and the aquatic system for our fish. So having a hydrological model or a better understanding of our hydrological response is so important. And not to mention that given our small islands, we have those very flashy systems on the right, which you can see that we have the new national 24-hour rainfall record that happened in Kauai. So the total rainfall is 49.69 inches in last like 24 hours. And then you can see that the flash flood, I'm happy to share some of the video that we can real-time recorded that how fast the water coming down and how much damage it could pose, like you see on the bottom right picture. And as Bart was hinted at in the beginning of it, that to build this hydrological model or do hydrological modeling have its own challenge in terms of like a data availability. And specifically, if you see on the left that building the hydrological model, the first thing we need is having those data. And in many times, and in most of the cases, the data have gaps. We don't have enough length of data, and it make those building of model very challenging. And something also to hint at is that there's a lot of times that we don't have enough gauges to describing the hydrological response. So a lot of time we rely on the hydrological model to help us to estimate those discharge on those ungauged streams. Next slide. And to drill down to give you a more concrete example that this is a watershed right on Oahu, one of our busiest tourist islands, and at Honolulu. So you can see that that's the Alawai watershed on the top left and also on the right. And that's right above the most tourist location, Waikiki Beach. This is the Alawai watershed. Something I want to point out to you that this on the left, that's the watershed have 3 streams from Makiki, Manoa, and Palolo, and I drain it down to Waikiki, where at the bottom of the picture. And if you look at the color on the top left picture, the back of the north of the watershed is the back of the watershed. It has a rainfall, annual rainfall up to 3,932 millimeters, about 155 inches. Well, when you close to the shore, it's about 549 millimeters, about 22 inches. So that speaks about the variance or the gradients of the rainfall just within this watershed. And just to give you a little bit more scale perspective, this watershed is about 32 square kilometers. So it's really not a big watershed while they have such a big rainfall gradient. And give you another perspective is from the right, you can see that this is different gauges that is looking at the storm coming down. So on the top, the rainfall showing that the is about 160 millimeter rainfall coming down in 8 hours. And at the bottom, at the back of the watershed, which has the red, pink, blue, green, and all the way to the almost the river mouth is the brown color of the dot. So those are the gauges that we have in this watershed. And if you look at the x-axis of the timing, so for this 170 millimeter, 6.7 inches of storm in 8 hours, it takes the water 30 minutes only from the back of the watershed all the way to the river mouth. So we really don't have a lot of time to respond or to describing the storm coming down. Next slide. So here, and I don't think I have too much of time, but I just want to point out that, so from the spatial scale that I'm talking about within this very small, well, not that small, but it's a not big watershed, and that's the rainfall gradient that we are seeing. While if we are using those big climate data, for example, if you see the grids on the left, on top of the watershed, I put the grids on about 1.5 kilometer cells, which is the downscaled climate data we have here. You can see that we probably get only 14 cells to represent such a big gradient from the back of watershed all the way to the river mouth. And then on top of that, the temporal scale of the hydrological response, like I said, is take only 30 minutes from the back of water, for water to come from the back of watershed all the way to the river mouth. So there is a spatial and temporal scale mismatch if you can see that. Next slide, thank you. And next one. So I just want to use this slide to summarize what I want to provide here, that we have a lot of property, business, and human life to protect, to use, and then of course I can't forget my fish that I mentioned earlier that we would like to protect and understand using the hydrological model that we like to use and model, while that we are finding those mismatch of the climate data to fit into our hydrological model. So here, just to summarize that this is something that I know that I really like to work on, continuously work on, and then Waterhackweek has been really helpful in terms of helping me understand what's the data availability and what's the tool out there. And I'm happy to talk more about it. Thank you. And I believe Christina has something to add after this.
Thank you, Yunfan. Yes, this is a perfect overview, I think, and introduction to the slides that I wanted to share with the group, just to give additional context. I know there's people coming to Waterhackweek and who are interested in linking the whole scale of data, like what Bart showed, through using models like what Yunfan showed, to really understand how to design all of the research steps that go through those workflows, so that we can use it, for disaster preparedness, for example. For me, is sort of the quickest time turnaround and the highest resolution needs that you could imagine using these types of data sets for. So I just wanted to bring up a new National Institute of Health Disaster Research Response Initiative that is looking at addressing this issue of disaster research as a area of convergence that we can maybe build on or adapt our tools to make it useful for questions in the disaster research domain. I know for hydrologists in the group, or people who have some experience with computational models, there's already so much environmental chaos that we study. When we layer on top of it the physical infrastructure, and then the social systems, and then the organization of groups, and then throw a hurricane at it, that type of being able to simulate and understand, prepare for that amount of chaos is a huge challenge of the day. And one way that we're, the National Institutes of Health and NIEHS are building, for example, these experiments. They've done exercises in Los Angeles, Houston, Boston, and Tucson where they set up a disaster research response workshop where people come together from these local areas or cities with governments, tribes, the city, the county, the federal agencies to experiment and drill on what would happen, what would we do if as a disaster hit this city. And so in Seattle, we have a workshop like this that's in the planning stages for next year. And I think that provides really relevant and timeliness for Waterhackweek and thinking about how to bring data together. In the case of this workshop, it's going to be focused on the big one, which is an earthquake. And the scale of the exercise really, if you have an earthquake, what is that going to do to the water systems? What time of, how is it going to impact the coastal systems? If the water treatment plants all go offline, then what happens? If you look at communication and transportation failures on top of the environmental inputs that some of us, on the seminar are familiar with, that combination of impacts in that scenario really is interesting and really important for contributing to a cumulative approach to developing science and research together. So these types of workshops are, I think, what we learn at Waterhackweek of how to work together and how to build team experiments and projects that get at the multidisciplinary approach of looking at problems and building tools that apply across common problems for use in other disciplines is really important. So I wanted to just give a heads up about that and the types of opportunities for a January workshop that's coming up. And also to think about if you have these amazing climate data sets, like what Bart was showing, and if you trusted the models that Infan was showing, how would you use it in your local, how would you use that information in your local community? And I know a lot of us people coming to Waterhackweek are from, our target is to have about half PhD students, which is what we'll have in attendance this year. But the other half of us come from all areas of research and practice around, working with water data and building software and research tools. So we'll have educators, we'll have people who have experience working with humans, so we call them, from the engineering hydrology point of view. And then, coordinating research across disciplines takes a lot of different sets of skills. So I wanted to pass it back to Stephen and talk to Bart and Infan about how do we explore research in a way that it really gets at the roadblock. Stephen may be still muted. So I'm going to keep talking until Stephen unmutes, and you can interrupt me.
Can you hear me now?
Bart. Yes, go ahead.
All right, sorry about that. I actually noticed we have a question in our chat before we address these points here. Looks like for Yinfan, does Hawaii have an early warning system for the storm events you addressed, and how reliable, if there is such system like that, is that?
Yeah, I'm happy to, can you hear me okay?
Yes.
I'm happy to address that. So, so we do have national weather services here on the islands, and then forecasting is responsible to forecasting all the coming storm and potential hurricane and everything. However, I hope that's not offending anybody, but usually when they passing the warning is like island-wide and or statewide. It's not be able to address that specifically watershed or anticipate any kind of variance across the region. So I think there's improvement can be done on the forecasting for sure.
Great, thanks. That sort of leads into another question about, you know, what do you, I guess for both of you, what do you see as the biggest research gaps with using data sets, whether forecast or reanalysis climate data or any of the data sets you talked about at the scales they currently exist at, you know, at multi-kilometer scale versus getting them down to that smaller scale where they can be more informative to these small scale processes, you know, for different applications. So what do you see as sort of like the data science or scientific research gaps there?
So who do you want to go first?
Either one of you.
Well,
Bart, go first.
okay, sure. So, I mean, the reality is that, you know, these gridded-based products, if they're based on station observations that are interpolated, station coverage is not all that high, right, for most locations. And the reality is also that a lot of stations tend to be in areas where there's a lot of people. But that's not necessarily where the hydrological processes are most active, right? So here in the Pacific Northwest, you have uplifting of air masses over the Cascades. The biggest gradients or the biggest changes in precipitation happen in the foothills of the mountains. That's not necessarily where most of the stations are. So similarly, when you look at these gridded products, they just kind of limits on the resolution of these remote sensing instruments that are used to estimate precipitation. And on the models, they just limits to the amount of computing time that we have available to run at higher resolution. So I think there's a couple of areas where adding local information to these kind of coarse scale products remains a challenge. And I don't think that there's a silver bullet that suddenly, you know, we figure out exactly how to do that. There might be some new opportunities in some of the machine learning algorithms for, you know, that may provide a way of transferring techniques or findings from areas where you do have high resolution observations to areas where it is less so. The other one, I don't really kind of know. I mean, the challenge of kind of linking these large scale patterns to higher scale, small, coarse resolution weather data to kind of like local problems, I think that is just kind of a challenge. And it's something that probably you have to kind of more explicitly incorporate when you look at the uncertainty of your predictions.
And I will just add it to what Bart just said, that I think, like he said, that there's uncertainty or bias in some of the large-scale product, and how can we, using whatever method out there. For example, I had a colleague from Switzerland come to our watershed, actually trying to use stochastic and machine learning, trying to simulate the rainfall patterns and movement when the storm coming in. And that could be a potential area to explore, and then to describing the bias when you come to the rainfall, because after all, the rainfall is so important when you try describing the hydrological response and the process. And another thing that I want to again point out is that the scale, spatial scale from the meteorological data versus the local scale that we're trying to, a local scale like problem or issue that we try to deal with, there's still some mismatch there. So how can we address that? And not to forget, hydrological response still largely depending on the characteristic of the watershed, right? So the impervious surfaces, the type of topography, the size, the shape of the watershed. So I think there's still a lot of things to explore, and how can we better use that information to inform and better use the data available.
Great, thank you both. And I think you mentioned uncertainties there. That's, you know, our first question here was, or listed on this slide is, yeah, how can we accurately quantify those uncertainties? And I think also really important, how do we clearly explain those uncertainties to the general public, and both through just how we write about them or talk about them, but also I think that can also be a visualization sort of questions, like how can you visualize just on a simple plot, you know, uncertainties and a model output or something like that. I think maybe we can end here for this slide and move on. So hopefully all this discussion has given all of our attendees ideas about Waterhackweek, things they might hope to learn or practice through projects. Here's an example showing the curriculum from last year, both Cyberseminar topics, the in-person trainings, which were the tutorials at Waterhackweek, and then you know, the project work as well. If we go to the next slide, you know, just pointing out that the next cyber seminar next week, March 5th, we'll be talking about projects, introduce, you know, what the purpose of those projects are in the context of everything we're learning at Waterhackweek, the typical scope of a project, what those kind of look like. We'll review project guidelines as well, kind of the definition of all the details there. And then I'm also going to share in the Slack channel, we have a project brainstorming Slack channel. I'll share on there links to past projects. I can also share it in the chat here on Zoom. So you can kind of get an idea of what these projects look like. And if you have ideas, you can start discussions on Slack before arriving at Waterhackweek. And not everyone needs to arrive with a project or a data set. I mean, because you're free to join other people. And if you see something someone's talking about on Slack that's interesting, you can reach out to them or reach out to us if you have any questions or ideas that you want to brainstorm a bit. And then on the 12th, the cyber seminar, we'll be talking about tutorials. And we want to know, do you have something you'd like to teach in a sort of mini tutorial, or are there specific things that you want to learn more about? There's a Slack channel for discussing this as well. And there's a Google form link in that Slack channel to sign up if you want to pitch a tutorial topic. And you can pitch that actually during the cyber seminar on the 12th, kind of give an introduction to the topic and see if anyone's interested in learning about what you have to offer. Next slide. So we want to invite all of you to think about projects, take a look at the past projects, the links to their GitHub pages, as well as the past cyber seminars with, I guess we can provide links. I'm not sure exactly where those links are, but we can provide
They're
those.
all on the, they should be on the Quasi Cyber Seminar web.
Oh, okay, all the videos from last year as well.
And there's a website, the schedule website on the Waterhackweek website also has the links.
Great.
So the other thing about the tutorials and signing up for pitching a tutorial, and also, you know, encourage people who who might be attending remotely to are also welcome, and the Google form is for people who want to pitch the tutorial during the cyber seminar, and then until we arrive at Waterhackweek, we will be trying to get an idea of which tutorials we're calling them floating tutorials, and we'll sort of adapt what we do on Thursday to be as relevant to your projects as possible. So that could be a new tutorial that's just, a new tutorial about a paper and a tool that just came out, or it could be a new function in a tool that everyone's using that we didn't know about. So it could be related to a project and solving a particular problem that comes up during the week, and we just want to have that flexibility to make Thursday's tutorials accessible to as many people as possible and useful as much as possible. So this is the 1 minute of the Cyberseminar that we do a public service announcement. And in our, the Waterhackweek and it's a workplace, and we don't have a lot of time for professional development. Sometimes there's trainings that might take a whole day or multiple hours, and we just don't have a lot of time for it. So we're experimenting with just inserting professional development type topics in shorter time spans and just one topic at a time. And one thing that's come out in the past couple years is this concept of splaining and trying to understand when you are making an assumption that someone doesn't know something about a topic, or that you know more about someone else about a topic. And that, I think you may have heard about splaining in the context of mansplaining. In 2010, that was the word of the year. So it's been about, 10 years of that new word existing. And this figure is a gender neutral version of that, in the sense that I think it's useful to consider that we all, especially in diverse groups and with new people, you may make assumptions about what people know or where they're from that ends up being embarrassing or could be distracting for them, but you don't realize it, or once you do realize it, it causes some miscommunication. And so I just wanted to bring up this tool that came out a couple years ago, that an educator was asked just to explain to us how do I know when I'm explaining to someone something about what's happening. So a great example could be that I know that I struggle with this. This didn't happen last year, but it wouldn't be completely in the realm of something I would do. I might start talking to you about my vacation to Hawaii and all the different things that you should be doing in Hawaii and how great it is, and I'm just meeting you at the first coffee, meet and greet, and I didn't make the assumption that you're from Hawaii and you didn't ask me about Hawaii, or, and you obviously know way more about Hawaii than I do, and then I end up being embarrassed. And you might not really you might make assumptions that I'm going to make that type of assumption about all different, topics that you might know about. And then I would like to avoid that in the future. So watch out for hydro-splaining, pi-splaining, bit-splaining, meteor-splaining. I just made all of those up. But I think that if you do end up splaining, or if I do to anyone, you're invited to please let me know, and I will stop talking. The final parts of the seminar here is just a reminder about the other quasi-workshops going on. There's, you can learn more about, March 25th, precipitation estimation and analysis of remote sense information is specifically great related to today's topic. And also, I think tomorrow is the deadline for this WARF Hydro training workshop, which is an amazing model to learn about. And that is the computational workhorse behind the national water model. So that's a really useful workshop. Then the other announcement, the disaster research response workshop that I mentioned earlier in the Cyberseminar, that is a workshop that is going to be happening next January. in Seattle. So if you are working in the area of health or water-related health or disaster, this type of exercise and being involved in the workshop is, there's still time, lots of time to get involved, learn more about it, or bring this type of workshop to your community. So we have the workshop coming up in March 23rd, and we are going to keep, checking Slack and, as responsive as possible on Slack with all of your questions about coming to Seattle and visiting. And I just want to mention and acknowledge the Waterhackweek learning community and our founding cohort from 2019. Bart and Yimfan, do you have any last words about your experience at Waterhackweek last year and what you're looking forward to for this year or next year for you, Yimfan? Bart?
No, not really. I mean, I was an instructor, so I'm not sure. Yeah, I'm not sure what you're looking for.
Okay.
I want to say enjoy the spring break and enjoy the beautiful weather.
Thank you. We will see you back here next week, Thursday, 10 o'clock Pacific. And thank you to all of our sponsors. If you are interested in collaborating or sponsoring more with Waterhackweek this year or next year, also feel free to contact us and we can add you or your supporter to our sponsor list. We'll see you next week. Thank you. Thanks, Stephen.